Thank you. A microphone is on? Okay, thank you. Thank you, and thank you, the organizers, for the opportunity, and especially in this event in honor of Jack, Professor Hale. I started my graduate study day one when I went to check in with my professor, Professor Jianhong from Hale University. He told me Jack Hale is coming to China to give serious lectures in Nanjing and Shanghai Fudan University. That was 1984. So he made a copy of a huge number of manuscripts that Jack sent to Professor Wang and suggested that we really should read all those stack of papers while it was the first day on graduate school. So we started from chapter 5 of Jack Hale's 1977 book. That's, I think, the most difficult chapter on dissipative dynamic systems. And the first research paper I read was a paper sent by Jack Hale to my supervisor. It's a joint paper with Jianhong and Jack Hale on infinite delay differential questions with infinite delay. So I would manage to understand that paper and try to extend it to neutral differential equations. So I shared this with Jack Hale, and after a few weeks, I received his comments. It was marked annotated on my paper, almost every line. Not only just mathematics, a lot of English and grammar changes. That speaks of the fine reputation that John mentioned, how Jack is supportive of young people. My second experience with Jack Hale was I came to York University as a new faculty member in 1990. And after I accepted the offer from the university, my postdoc mentor, Herbert Friedman from University of Alberta, he said, Jianhong, the Canadian Industry Applied Mathematics is looking for the next slide for his annual meeting. I think you should do it. He should organize it. I told this is too tough. I'm new to Canada. I'm new to the university system. And Herbert Friedman told me it's an easy job. So that was the first lie and the only lie Herbert Friedman told me, but I accepted. The first job as organizer is to really set up the academic program with support from Herbert Friedman. And so the first person I approached was Jack Hale. So I asked Jack Hale if he was willing to come to Toronto for a plenary lecture. And Jack replied right away. He said, John, the time coincided with the meeting in Lisbon, in Portugal. I would really have to rush from Lisbon to Toronto. I was so innocent in that time. I really didn't know how difficult it is. So I told Jack, it was, to my knowledge, the first time the native differential question is going to be designated as a special thematic session of the annual meeting. We really needed help. And Jack said, yes, I would come. So that again speaks of the support of Jack to the young researchers. I benefit a lot from Jack's support over the many years. And today I really did not know how many of you have attended my previous talk in recent months. So I decided to give a very generic title to make sure nobody is going to waste 50 minutes of not listening anything new. So I would like to talk about a sorted problem, innate differential equations, but we'll focus more of incorporating the behavior adaptations along with the population dynamics, either in ecological or epidemiological systems. So I'm going to really talk about couple system of traditional differential equations with algebraic or integral equations. So I hope to touch on 3 different components. Maybe I'm going to skip one of them. So in the first part, I'm going to talk about how to incorporate the human's behavior adaptation to the real or perceived risk during a pandemic. And I would like to see how this coupling along with the public health intervention logistic delay are going to generate multiple waves of a pandemic. So this is in collaboration with a couple of postdocs, Professor Jianhong and Professor Scabrada. They are both now faculties in China and the UK, but along with Kumamuti, you heard his talk today, opening remark, is algebraic number system. But why he was involved, because Fields Institute is perhaps, it is the institute that commissioned perhaps the first international national modeling group providing the mathematical analysis and predictions in support the pandemic decision making. This national group was funded here at Fields Institute on February 14th of 2020. That's way early before the COVID-19 became a public risk. And Kumamuti is the one driving force for this national team. If time permits, I was going to talk a little bit about another types of behavior adaptation, that is the vector attachment and the feeding behavior adaptation in response to the host grooming behaviors. So I would like to see how this couple system of the population of the vector host interaction along with this vector behavior adaptation going to generate multi-stability in the chicken population dynamics. This work is already published. And then we're going to talk about how those problems motivate and call for more general setting of studying the global dynamics of semiflows, which are monotone, I put a quotation inside, with respect to high rank counts. So this is based on series of papers in collaboration with Li Ruifan and Yi Wang from Chinese University of Science and Technology. So let me start with the first one. So this is a typical epidemic curve of the pandemic. And this is the time series of the reported cases in the province of Ontario, this province, in the first 2 years of the pandemic. This is not the entire curve. The pandemic is still, the COVID is still maintaining a persistent level. But I want you to pay attention to the first year. So this is the year when really the population has not built up its herd immunity. This is the year we did not have the medical intervention. We don't have vaccine. And this is the year the disease has not mutated. But despite all this, we have observed 2 waves in the first year. That's in the middle, from here to here. Okay, so this is not single phenomena. I'm sure you have experienced all of this, and this is not singular in this province in Canada. Canada is a federal country, so we have multiple provinces and territories, and many of you have done and followed the curves. And different provinces have different governing parties. They have different idealism, and they have different way to enforce, implementing public health interventions. But despite all the difference, so each province has gone through this curve. Okay, so this is not unique, and there's multiple waves occurred in a single season. It's a common phenomenon. And this is also not unique in Canada. And if you don't believe in the number of reported cases, you can look at the second picture. This is from France, and this is based on the wastewater surveillance. And this is reported from a paper by Henry Brzezinski in the scientific report. So there are multiple curves represent different regions along the Sina River. In the first year of the pandemic, you can see also after the first wave, there is a shortened transit behavior, and then the number of cases spike. And again, in different regions, there are different public health interventions, and you can see all have similar behaviors of the second wave with larger amplitude, and then sustained it in a oscillatory fashion along an equilibrium which is not supposed to be there if we're using classical epidemiological model. Okay, and Timo, what should we do? And number. I have to wait until my colleague Brian's coming. I want to show you that actually this is not also unique for only. Brian, don't go. Thank you very much. I will make sure not to touch too much. So this is not unique for pandemic, COVID pandemic. This was the case in the SARS. This is the SARS-1, 2003, 2004. This is in the Greater Toronto area. So in almost every region hit by this SARS-1, except Beijing, of course, and we had experienced 2 waves. And within a short period of 3 months. And that case is the second wave had lower amplitude. And this is the case on the right-hand side is influenza pandemic. This is a picture from the Shanxi province, and this is based on the hospitalization data. So we have hospitalization data, you have case reporting data, wastewater data. They're all showing multiple waves in the single seasons. Okay, so we're trying to see try to understand the phenomena. So the Fields Institute was involved because this is a constant, it's a questions constant imposed from the medical and public health communities. So, so we started with the transmission dynamics. So I'm going to start with the simplest epidemiological model, SIR model. We have susceptible, infected, and recovered, the simplest possible case. And I'm going to consider the situation corresponding to the early phase of the pandemic. So you don't have the herd immunity, you don't have the vaccinations, and the disease has not mutated. So, and because the population has not reached the herd immunity, so I can simply assume susceptible population remains to be relatively constant. So I have a very simple transmission dynamics model for the first phase. So the change rate of I is equal to beta times I of t minus gamma I of t. So the second term minus gamma ILT is the removal rate of the infected individual from the population. But the first part is the so-called incidence, the number of new cases due to the contact of susceptible with the infected individuals. The coefficient beta, the coefficient at the moment, beta is the number of contact per union time times the transmission probability per contact. Both can be changed. Both can be changed. The number of contact can be changed. The transmission probability can be changed by, for example, wearing mask. Okay, so now I'm trying to couple this towards the behavior adaptation. So we're going to make a standing assumption. The disease transmission effective contact rate, that is contact rate times the probability of transmission per contact. That rate changes as individuals adjust their behavior according to either the real or perceived incidence. And the higher the incidence, the smaller the effective contact. So this is a phenomenological model. Of course, the behavior change induced by disease severity should also be considered. It will be considered in a moment. We're going to explain what do I mean by perceived risk, what do I mean by the delay. And therefore, if I assume the effective contact beta is a decreasing function of incidence, I know incidence beta is beta times I, so I get a simple phenomenological formulation that beta of t is a function of the beta of t minus tau times I t minus tau. I'm going to assume tau is a delay. What does delay means? I'm going to explain in a moment. So this gives the renewal equation for the effective contact, the behavior adaptations. So the couple analysis is very simple. So it's very simple differential equations for the transmission dynamics or the dynamics of I. Very simple looking differential equations coupled with algebraic equations that govern the behavior adaptation. Okay, so there are two key nonlinearity and the parameters. One is about specific form of the behavior adaptation functions. So these are determined from a number of factors, including the population tolerance to the risk and the community flexibility for adaptation, and also what the perceived risk associated with the incidence means, how the population perceives the risk. And this form can be informed from many different ways, and most effective way will probably from the survey. So we had done some work with some of the best behavior scientists in US and Canada to understand how people respond to the availability of vaccine and also to the availability to the risk.
So people perceive beta times I are the rate of increase in the past, or the increase only perceive in the past the number of infected. I'm asking whether the beta t minus tau should be increased or not.
So I will come back to that one. So the question is whether should have a b beta t minus tau or just beta t, if you understand. I'm going to explain it.
IT minus tau.
Right. Yeah. So throughout the talk, I'm going to use this very simple looking behavior change function beta of t as beta 0, 1 plus k of beta t minus tau I t minus tau, since tau is there in both factors. For a moment, I'm going to explain. And the two key parameters, one is the k. So the larger the k, the larger the response in response to the incidence. And beta 0, of course, is the maximum contact you can have. So before I'm going further, so I want to show in this frustration from Newton, and he, at a late time of his life, he invested a lot of money on some stocks, and by the end of the South Asian bubble, he lost all his fortune, and then he made this statement that when you try to model the madness of humans, and he feels that it's beyond his capability. So that's what Newton said. But I think now we have a better resources to try to understand the human behaviors. So we have started a project really incorporating the machine learning along with the transmission dynamics, the building so-called neural differential equations, to help us to be able to identify the behavior adaptation to the perceived risks using combination of AI and symbolic manipulation to track this behavior adaptation in real time. So this is the first paper already published in Journal of Theoretical Biology. This is not my focus today. This sitting is called the neural differential equations. So let me go back to the coupled system. Please bear with me in a moment. I'm going to explain why this tau should be appear in this way. So I have a differential equation for the transmission dynamics coupled by algebraic equation for the renewal of the behavior with time tau. And I'm going to assume that, of course, this behavior adaptation function f0, when there's no infections, this is the maximal effective contact number per time, union time. This would be the number of effective contacts before the pandemic level, for example. So if I do that, of course, the beta 0 divided by gamma 0, by gamma is the basic reproduction number. That's a threshold. And if this number is larger than 1, then you would see exponential growth of the infections at the very beginning. And I'm going to assume this function is a strictly decreasing function. And therefore, what does mean? Because of monotonicity, then for every given x, I can solve these equations for b. So I get a function of b of x. So now, of course, if x equal to 0, I know my b of 0 is the maximum value of f of 0. And this is a decreasing function of I, and then I substitute b to I, then I plug in into algebraic equation for the behavior adaptation. I should be able to solve for the equilibrium of bi star equal to gamma, and that will give me a non-trivial equilibrium of I star, which is the infected levels, infections level at the equilibrium beta I star is the contact, if transmission effective contact at the equilibrium value. So already this is a this phenomenological, the simplest possible phenomenological model has already told us something different than the classical epidemiological model. First of all, the classical epidemiological model says that because the herd immunity and the number of susceptible is going to decline, and eventually the outbreak is going to die out. So the only equilibrium for SIR model would be the trivial equilibrium when I equal to 0. But in this case, the I is going to reach to a certain equilibrium. Okay, and at the equilibrium, the contact is simply nothing but gamma. So at the equilibrium level, you have base contact effective number, the effective reproduction number equal to 1. So we're talking about the pandemic stabilized at the situations, the reproduction number is always around 1. And there is the equilibrium value here. All right, so to going further, I would like to simplify the study a little bit. And I'm going to assume actually this function f is given by a family of functions. I'm going to parameterize this function in terms of fixed capital F, but times k times x. the reason I'm doing that, then the derivative of f at 0 is equal to k times the derivative of capital F at 0. So I'm going to use the k to really describe the flexibility of the community for behavior adaptation, and the larger k, the larger the flexibility. I call the community plasticity. One of my friends told they don't like the plasticity name, is more for physics. I should use the flexibility. So k is really tell you how flexible the community is. Okay, so so I don't want to go into further here. And so what is the importance of this k? So that's now starting coming closer to the question Thomas raised, but how tau should be entered, what the form of tau. So there are different ways the behavior changes in terms of the real or perceived risk. So if you assume your population changes behavior in terms of incidence, but incidence is beta times I. So that's the daily number of new cases. Okay, and here is not really the cases is not reported. So it's reported cases. So there's already one delay respond to that, because your risk to the public is the reported case. That's already with the delay from the exposure of the infections, and that's one delay. And then you have to implement your behavior adaptation. You have to implement the behavior adaptations. So there are two. So K is relevant to the how flexible you are, and delay in this case is the sum from exposure to reported, and from reported, and then you realize the risk and implement the public health interventions. Okay, so that's the sum. So in this case, if that's the first case, K, what is K? So you can in the case where my F is using that simple looking rational function, then this K basically say so when the number of reported cases reach to when the incidence reaches 1 of k, then you're going to reduce your contact from beta 0 to original 1 to half of it. So this is really half capacity. The strength, how fast we reach to the capacity to the maximum. Now I'm talking about preserved risk. So people might not respond to the number of cases anymore. People might respond to the number of people in the hospitals or in the ICU admissions or the mortality. So that means that the perceived risk could be is the incidence beta times I with delay from exposure to infections to, for example, admission to ICUs, and plus you implement it. So what is the role of the government? The government is trying to facilitate the behavior adaptation and to try to speed up these public health interventions and to make the behavior adaptation happen faster than delay. So the delay plays a role here is to see how fast, first of all, how you communicate the risk to the community, but secondly, how fast you implement the behavior adaptations. Okay, so let me use these very simple looking functions as an example to really show some of the calculations, and my purpose is showing some of the picture, but more importantly, I want to tell many of the important mathematical problems that we could not solve during pandemic situation time. So for example, first of all, I know that if R0, that's beta 0 maximum number of contact divided by gamma, or times the number of infection days, is larger than 1, this should be 1 here, this should be larger than 1, then there will be outbreak with the introduction of new cases, And the couple system has a disease-free and effective contact change-free equilibrium. That's the disease-free and stay in the original contact before the pandemic. And this is equilibrium is unstable. Okay, and when R0 is larger than 1, then the system has a disease endemic equilibrium. Is to say that this is important. If the behave community is going to respond to the disease risk, then when the wave is over, the community structure is modified. So the contact is no longer beta 0, is already modified, and keep around about social economic structures in your neighborhood. You see that wave really has also modified the community structure in social economic activities, and the equilibrium, the disease is not going to disappear completely but maintain at a certain level. That level is completely determined really by the disease characteristic of R0, but also by the community flexibility. All right, so now our purpose is try to understand the mechanism towards multi-waves, but not only the mechanism multi-waves, but towards understand whether you're going to have escalating waves rather than damped waves or sustained waves, but also try to understand the distance, the duration from the first wave to the second wave, because those are quite important public health informations. So to do that, we linearize the system at the disease-free equilibrium, then have a linearized system. So this is a very simple linear differential equation. It's so simple that I even embarrassed to show you. The first one is a simple differential equations I, and the second one is a renewal of beta. This renewal tends of t minus tau hundreds, another Forsen term from the infection of t minus tau. Yes.
Before vaccination, or
this is before vaccination. So this is before any medical interventions, and this is before the disease has mutated. And this is even before the population has reached the herd immunity because of the infection or the vaccinations. Okay, so now you can linearize the system, try to looking for pair of purely imaginary eigenvalues. Remember, that's the only time this equilibrium is going to lose equilibrium. The system is reach the equilibrium when the beta is beta divided by gamma. The effective reproduction number is equal to 1. So the only way for this one to lose further stability and generate oscillations through the appearance of pair purely imaginary zeros. So this is not too difficult. If you play around the characteristic equation, which is the same for Dinae differential equation with negative feedback, even though you have formally coupled system. So then you have a critical value of Dinae. We can calculate it. You can calculate the frequency of the bifurcated periodic solutions. Then you can see all the phenomena using the parameters that is determined from the real situation associated with pandemic. So this is the case where you have Dinae, which is 7. So you can calculate Dinae 7 in many different ways. You can think about from the exposure to confirmation reported about 7 days, and you take action right away. Or you can then you would see a damped oscillations quickly to a very low level equilibrium, but you can also increase in Dinae to 11. If I have 4 days Dinae, you might be able to see oscillations, but oscillations in with a relatively low amplitude. Okay, and if you K is relatively small, and your Dinae is really the right range that at least in this part of the world, in this province, 14 days is probably the maximum you can achieve with our system. And then you would have escalating waves, eventually reach to equilibrium state, but you can see second wave have high amplitude and so on and so forth. And we can do that. We can also we also simulate the situation of COVID-0 implemented in very strictly in, for example, in China, then you can see really quickly sustained damped oscillation to invisible equilibrium state, but I don't want to go into detail about that. All right, so this is what we did so far only. And what is really interesting mathematics left is what's happening when the delay stay away from the first critical value. The critical value is about 10 in the range of the 3 simulations, so there is a critical value, and you can also have a sequence of critical values of delay. So this two, as I mentioned, remember the characteristic equation is the same as the characteristic equation for scalar delay differential equation with negative feedback. So we have already observed local bifurcation of sustained periodic solutions. You have escalated waves and then sustained in a stable periodic solutions. And can you see the global quantitation? What happens when that delay is getting larger and larger? And what's going to happen? So we did this before for scattered delay differential equation with negative feedback using the so-called global bifurcation theory, Hale bifurcation theory. And the key is we want to, if we try to substitute, if we're looking for k times tau delay, you want to have a boundedness for the period, you want a boundedness for certain periods. And the way to rule out certain periodic solutions in order to establish the periodic bound for the period, and then you need to locate xjt, which is I of t minus j tau. Now you have a beta change as well. So beta t minus j tau is a new variable yjt. And if that coupled system has a periodic solution of period k times tau, then I can substitute this state, the time, those variables into the coupled systems. I would get a coupled ordinary differential equation with some algebraic equations. I need to rule out the periodic solutions of such a coupled system of differential equations algebraic system. And in the case without algebraic equation, I think earlier study was done by using Roger Nussbaum's circulate matrices. You may be able to rule out certain pure solutions, or using James Modani and Michael Lee's compound matrix approach to rule out pure solutions. And we have not done this. So this is something I think we should look at to see whether how we can rule out pure solutions of this kind of coupled system of differential equations algebraic systems. And what is really important is looking for the structure global attractor, how the global dynamics look like. And here's what I think. So if we try to look at the solutions which are defined for all t, and especially those solutions starting from the unstable manifold of the positive equilibria, and then you can iterate that algebraic equation beta t to get a function beta t in terms of I of t minus tau, but also I t minus 2 tau, and so on and so forth. So you have this dependence of beta on the delay argument or the integer delay tau, and this function is strictly monotone with respect to all the variables. And you can write on the first equation is pretty much a delay differential equation with a negative feedback, but that feedback depends on all the integer tau. And what can we do? So can we really describe the behaviors of these delay differential equations? One of the potential technical tool is what I want to talk about is the semiflows which are monotone with respect to high rank counts. So this is based on, again, a series of papers with Li Weifeng, who was a postdoc with me, and he's now joined Professor Yuan is a faculty of Chinese University of Science Technology. So I have to explain this to you because I want to thank many of you for handling those papers, and there is a common negative comment about all those papers, and it's the monotonicity and by the cone. So I need really to explain why we use those words. So what is cone of rank K? The cone of rank K, first of all, if it's invariant, it's invariant and multiplication of all real numbers. So you know that it's not already cone anymore. So it's not invariant and only multiplication of positive, non-negative number, but and all real numbers. Right? Secondly, it contains k-dimensional subspace, and the maximum dimension of subspace contained in such a set is k. Okay, so k-con is not con then. Roughly speaking, k-con contains a linear subspace of dimension k, but no linear subspace of high dimension. So why I continue to use it, because it was used by other people. It started from Krasnevsky, and it was used by Lifshitz, by Sobolev, and in the serial dynamic system was really from George Fusco and Oliva in the early papers. So I have to admit, I know it's not a cone, but if it was called cone, a high rank, I have to use it. Otherwise, I will be inventing some concept that not really showing my respect to the pioneers in this field. Then there are some examples relevant to high rank accounts. So those of you work on zero number or monotonicity or no all this. First of all, if I have one dimension called the classical cone, so you take a negative copy of the cone, put them together is one cone. So that's why it's nothing too far away. It's sometimes in geometry it's called double cone. Okay, and two cone, if you take a one cone from three-dimensional space, you get two cone. Okay, and there are something related to cyclic existence. So if you have systems, you take sign change of the component. The number of sign change, if less than equal to k minus 1, then the set of all x in Rn with sign change less than k minus 1 is a k-cone, and in the differential equation will be a very natural cone I'm going to mention in a minute. And the difficulty with high rank cone is there's no convexity. That's the problem. When you try to pushing some of the results from semi-flow monotone with respect to cone to monotonicity with respect to high rank cone. All right, so we can define similarly by monotonicity. So since this is no longer order relation, it's not a cone. So when I call monotone, I invite lots of objection again, but again, I'm not the first one to use it. And Sanchez, George Fusco, Oliva, they all use it. So I have to use it now to avoid any further negative criticism. I always put quotation now. So we say x and y are related, are order related, because when x minus y is in this cone, I can define the strict relationship if x minus y is in interior with this cone. So I can now define a semi-flow is monotone if you're starting with order related pair, then the semi-flow remain to be order related. And similarly, you can define strong monotonicity with quotation again. And for that, a semi-flow which is monotone, strictly monotone with respect to high rank cone has some very nice property in terms of the omega limit set. And there are two non-trivial semi-orbit. in some literature type 1, type 2, but I would like to say one is that its orbit is eventually order related. So eventually 2 orbits are going to be order related, or not eventually order related. So type 1, type 2. And for type 1, so Sanchez looked at that before. And for finite dimension flow, which is monotone with respect to high rank cone, Sanchez proves that every orbit inside every 4 orbit inside omega limit set is always ordered. Okay, and Sanchez raised the question about what is the ordering property of the entire omega limit set of such a type of orbit, and that was raised in GDE papers 2009, and the answer was given first in the 2017 papers with Science Journal of Mathematical Analysis, and we have this trichotomy of omega limit set, and basically say if you have a pseudo orbit or pre-compact orbit which is eventually ordered, then one of the following 3 alternatives must hold. One is either omega limit set is complete ordered, first question, or is unordered, but then this omega limit set is contained in the set of equilibrium. There's third order alternative, which in finite dimension cases now we can rule out after some little bit regularity on the linear field. I don't want to go into detail. And if k equal to 2, if you studied restrictive cone to 2-dimension cone, cone of rank 2, then you have also Spankhara-Bendixson theory. So if I have long-trivial pseudo-ordered pre-compact orbit, and if the omega limit set does not intersect with equilibrium, then it must be a periodic orbit. So you have really the Spankhara-Bendixson theory with 2 cones. And what happens to the second type of orbit, those orbits which will never be ordered? Then those orbits are rare. This orbit is rare, and in finite dimension case, we do have results on the generic dynamic theory. I'm very looking forward to John's talk tomorrow. Everything we're trying to do is trying to see whether how much we can push from the Diné differential equation with negative feedback to general sending flow, and we do have results that if Q is a set of orbit which is pseudo-ordered. So this generic dynamic theory says that the set for X in the phase space either such that the orbit is either pseudo-ordered. If you have pseudo-ordered, we know its omega limit set is has limit set trichotomy, or omega limit set synchrotron. This contains open and then subset of the phase space. So that's a generic dynamic theory. This is established so far for finite dimension space. We know this is true for infinite dimension space. So far we have done that for infinite dimension space, but relies heavily on Peter. You have to encourage a student to really publish the thesis. Without that, we have to invent something new, which is not fair game for him. We do have an alternative approach to expand this result from finite dimension space to infinite dimension space. But the technique is really due to this brilliant student. I think he's now not in the academic community. So how does it relate to the global attractor I just mentioned? So see the picture with Diné differential equations with negative feedback. Thibault described. We still have a project started in 1998. I told Thibault if I wait for this paper for my promotion, I will never get my promotion. And we know from what Thibault mentioned that there is a sequence of Diné passing through which the unstable manifold of the trivial solution is going to increase its dimension by 2. You have a pair of purely imaginary zeros passing occurring. So I have the sequence of critical value of DNA for tau between these two consequent DNA. If you consider the sign change of the initial data, the sign change is not increasing. So that shows that if you define initial data such that we find the sign change is less than or equal to k, or 2k or 2k plus 1, depends on how, in this case, negative facts 2k. And we know this is a Kong of rank k, first of all. Secondly, we know the semi-flow restrict to this unstable, global forward unstable manifold is monotone with respect to this Kong of k. Right, so what I described applies to this problem, to this. And what I do not know is if I still have this, if I replace this one by single DNA now by sequence, by function of all DNAs at all the discrete multiple of time tau, can we describe the behaviors of the solution on the global forward extension of the unstable manifold? And if I want to use the theorem of the global or generic dynamics monotone with respect to, for semi-flow monotone with respect to Kong of rank k, then I would need to be able to create some Kongs which reflect this negative feedback, and just some preliminary thinking and to construct this. And once we have this Kong, we have the monotonicity, then we have some, at least phenomenologically we know, especially when tau is larger than the first critical value, and that's the next critical value, we know that will be a monotone flow with respect to Kong of rank 2, then we have a Van-Dixon theory. So this is not done yet, and I blame everything for pandemic, but this is really a challenge problem. I don't want to go into the second, the third component of the work. And I just want to mention that by coupling the behavior adaptations to the population dynamics, either through an ecological system, which I would like to mention today, but I don't have time, but coupled with epidemiological systems, I get a natural DNA differential equation coupled with algebraic system, or integral equations if I had the time to go through the ecological model. And this, I believe, is really a special case of what Otto is building. I received some recent manuscript from Otto, and he already started really build a very general framework for coupling behavior adaptation with population dynamics, and this really gives us to a coupled system of differential equation with a discrete renewal or integral renewal, and much of what I have been doing on DNA differential with a single DNA with positive negative feedback need to be expanded, and hope I don't want to promise like Thibault, but in 4 years I may be able to provide some progress report. Thank you.